Okay, this screen recording is going to show you how to use Orcad to do a Monte Carlo analysis. Here I've got a circuit that you should recognize. This circuit is an emitter common amplifier, and we have a constant current bias. Now I'm going to run a simulation to get the precise value of the base resistor to work out what value we should have. So I'm doing a DC sweep, global parameter, R bias, between 1.3 megaohms, 1.5 megaohms in 10k steps. As soon as I hit simulate, I now have a drawing window come up, and Orcad has calculated this graph. I can read off from this graph and find the value of where it hits 5 volts. It's about 1.455 mega ohms. What I'm going to do as well, I'm going to evaluate a measurement. Okay, I'm going to show you how you use some of these functions inside here because they're quite powerful. Here we have x at nth y. So x, V out, when it equals 5 volts and the first time that it equals 5 volts. Click OK. We've got a computer calculation, so it's actually measured that point given that function. This is called a goal function. 1.455. Back to Orcad capture. You see I've already put that number in as a parameter, and this component has already been set up to operate with that value. So I've already calculated the bias. The bias should be 1 milliamps. We should be set at 5 volts. Everything's working very well. What I'm now going to do, I'm going to delete these two components, I'm going to delete this first component, R1, and I'm going to put in there a component that we can vary its tolerance. So we're going to add a component. Now the component I'm going to add is R break. Okay. Rotate that round and drop it in place. Okay, I need to add a value to this, and that's this default value, 1.455 mega ohms. Okay. Now what I need to do, this is a specific breakout component. I need to go to edit the PSpice model for this component. So edit PSpice model off the menu, or you can right mouse click. We can go from either menu, we hit edit PSpice model. Okay, you now see that we've got R break star, and we really want R bias. That's what we called it before. So I'm going to give this a new name. Okay, so I'm going to left mouse click here twice, and I'm going to call it RB. Okay, that's what I'm going to call it. I'm going to hit enter. You notice that the name over here has changed as well. What I'm going to do is I'm going to go into our bias, save changes to RB, yes, that's okay. And what I'm going to do is I'm effectively going to copy all of these parameters here, which is what I set up before. I'm using Control C to copy them. Going back to RB, I'll delete that bit, Control V, paste them. So I've now pasted in. Let me just explain what these mean. R equals 1, the same value as what's on your screen. In this case, 1.455 mega ohms. Deviation by 10%. Temperature coefficient 1, the linear, 0.02. Temperature coefficient 2, quadratic, 0.0045. We have now added RB to the library as a model. Okay, I can click close. So RB is now set up and ready to go. Okay, and that's on our circuit diagram. So now let's just hit save. Let's go to our simulation. We're going to do this time a time domain waveform for 2 milliseconds at 10 microsecond resolution. Okay, I've turned the input voltage to 0 because I actually want to look at the DC levels. Okay, so I'm not looking at anything else. I'm not running Monte Carlo yet, although I will do in a moment. So Monte Carlo is not turned on. Let's hit simulate. Hopefully everything should work and we should have a straight line at 5 volts, which is exactly what we have. Let's go back to our schematic diagram and let's work out how we can add in the Monte Carlo parameters. Monte Carlo, let's turn it on. We're doing a Monte Carlo simulation. We're going to have 10 simulations. Right, let's make this a bit more interesting. Let's have 50 Monte Carlo simulations. We're going to use a Gaussian distribution rather than a uniform distribution. We're not seeding this simulation, so we're just going to let it just generate some random values, and we're going to store all the information. Okay, you can store every 15 or every 10 or whatever you want, or whatever. I'm storing everything. Let's click apply and OK. So now when we hit simulation, we're going to run the Monte Carlo simulator, so we're running it multiple times. This is what has come up now in Monte Carlo. We've got all these possible simulation results, okay, and we're going to plot them all together. They're all highlighted blue, so they'll all come in. Click OK. As you can see, we now have many lines on here because Monte Carlo has picked randomly throughout the potential, with a Gaussian distribution curve on it, the values for the bias resistor, and that's caused these DC levels. This is hard to analyze, so let's go and do a more complicated analysis. X-axis. In the X-axis tab we have performance analysis. Let's click on the performance analysis and OK. So now at the top here you see we've got histogram. So what we're going to do now is we're going to try and plot the DC level at any point on those waveforms at the bottom to determine what the histogram looks like. Now, as we had a Gaussian variation, we should have a Gaussian variation here. Trace. Add a trace. Let's turn off everything we don't need. We're only interested in voltages, V out, but we don't want to plot the entire value of V out, we want one number. So I'm using this goal function, maximum of V out. Click OK. And here is our distribution. Okay. Now it doesn't look like a perfect Gaussian distribution because it's random. If yours would look completely different than this one, that's the whole purpose of Monte Carlo. We only did 10 simulations, so we've been quite efficient, and we can see from that we have the mean value of 5 volts, which is what we want. The minimum voltage is 4.6, and the maximum voltage is 5.3. When you're within 1 standard deviation or 3 standard deviations, you can see the spread. So you've got sigma, standard deviation, or 3 sigma, the tails right at the outside. So you've got some probabilities of where the voltages will lie. Now, I don't think that's good enough for the moment, so what I'm going to do, I'm going to go back to my Orcad simulation, and I'm going to ask the simulator to do some more. Let's go silly. Let's have 1000 simulations and let's see what happens. Orcad is doing a great deal of simulation now. You'll see down the bottom here, 30–40%. It's an awful lot of data that we're storing. We can be more optimized. We can select only the voltages that we're interested in. We've got all of that data inside here. Click OK. As you can see now, we have a huge number of voltages plotted, anywhere from just above 4.4 up to 5.5. Let's go to our plot, axis, performance analysis, OK. Let's go to trace, add trace. We will add the maximum voltage at V out. Click OK. As you can see now, we really do have something that looks very much like a Gaussian distribution. So we've been a lot more accurate. If you wanted to as well, we could select this waveform, we could delete this plot and only look at the one plot. But this actually does tend to show you quite reasonably what's happening when you vary one component. In this case, we've effectively proven with a 17% variation in sigma to the input voltage, or to the main target voltage, that the constant current bias is far too well spread. This is a very wide curve. We would want a much tighter curve, okay, which would effectively represent the fact that the circuit is immune to variations in component value. For example, the potentiometer bias. So I hope that's been a quick introduction to Monte Carlo simulation. I hope you've got something useful from it.